Hello, welcome to my talk on potential flow theory for incompressible flows, Part 1, the principles and equations. In this talk, I will first introduce the basic assumptions for incompressible potential flows, then to make the introductions on understandings to the irrotational flows. And then I move to the velocity potential function and the corresponding Laplace equation. Then the boundary conditions for potential flows, and for the Bernoulli's equation for incompressible potential flows. Generally, for building the potential flow theory, there are three assumptions. Some are essential, while others might not be necessary, depend on the situation. The first and the most important assumption is that flow is irrotational, or in other way, the flow has no circulation around any closed curve within the flow. The assumption for irrotational flow is given by the core of the flow velocity vector is 0. And this will also lead to a velocity potential function, and from which three velocity components would be degenerated to a scalar function, phi. The second assumption is the flow is inviscid. This is essential, but this also be redundant, since when we assume the flow is irrotational, that means the flow is inviscid. For inviscid flow, the simple expression would be the fluid viscosity mu is 0. Therefore, the four Navier-Stokes equation would be reduced to Euler equation, as well as the Bernoulli's equation, as an integral form of Euler equation. Bernoulli's equation is the most used equation in fluids. And we may need to assume the flow is incompressible. The mathematical expression for the incompressible flow would be given as the divergence of the velocity vector v is 0. This is only applicable when the flow velocity is not very high, and this assumption would lead to the Laplace equation for the velocity potential function. We will see the details on this. Here, I must emphasize this is not an essential assumption, since in high-speed potential flows, the flow can be compressible. I will make a talk on that in the future. Based on the assumption of irrotational flow, the core of the velocity vector is 0, given as this. And we can calculate the core of the velocity vector given as this determinant. Here, the unit vectors I, j, k are the unit vectors around x-axis, y-axis, and z-axis respectively. And the detailed calculation of this determinant would be given as this. That means the core of the velocity vector is still a vector. We have three components around x-axis, y-axis, and z-axis. See here the unit vectors. So the component around the x-axis is this, and the component around the y-axis is this, and around z-axis this. To make this vector to be 0, that means we need to make all three components are 0. Thus, we have three equations. See this. So we can see, by assuming the flow is irrotational, the three velocity components u, v, and w are no longer independent of each other, but linked by these equations. Here we can also see, for three velocity components u, v, and w, we have three equations here. Can we say these three equations are complete for these three velocity components? To answer this question, we will see the irrotational flow in 2D case in the next slide. In 2D case, the calculation of the core of the velocity vector is still given as this, but we must take the velocity component w is 0, and the partial differentiation with regard to z would be 0 too. And if we look at this detailed calculation of the core of velocity vector, we can see this part would be 0 because w is 0, and this would be 0 too because the partial differentiation with regard to z. Similar for this and this. Therefore, in the core of the velocity vector, in 2D case, we have only one component around z-axis is non-zero, given as this. Therefore, to make this core of the velocity vector to be 0, we need to make the component as 0, given as this. So we can see in the 2D case, we have two velocity components, u and v, and they are no longer independent of each other, but linked by this equation. In here, we can see we have only one equation for two velocity components. That means to solve the velocity component in the 2D rotational flow, we need an additional equation to make the system complete. This would be different from the 3D case where we have three equations for three velocity components. So we can see a conflict between the 2D and the 3D irrotational flow. In 2D, we have two velocity components, u and v, but we have only one equation based on the irrotational flow assumption. While in 3D, we have three velocity components, u, v, and w, and we have also three equations from the assumption of irrotational flow. Therefore, we can see a conflict. In 3D, we have three equations for three velocity components. Can we say this is a complete dynamic system because of three equations for three unknowns? While in 2D, we have only one equation, but we need to solve two velocity components. That means we need an additional equation. Why we have such a conflict for 2D and 3D irrotational flows? In here, we will show for 3D irrotational flow, these three equations are redundant. For example, we take the first two equations, write this two equations as this and this. And we can calculate the partial differentiation with regard to x. So we have the expression as this. And similarly, for the second equation, we calculate its partial differentiation with regard to y. So we have the equation as this. And looking at these two equations, we find this term is same as this term because the order of the partial differentiation with regard to x and with regard to y is irrelevant. Therefore, these two terms are same. This means we would have an equation given as this. And we can take the partial differentiation with regard to z out of the calculation. We can have the expression as this. And we can integrate this into an expression as this. Here, c is an integral constant. It would be independent of z. So if we take c equaling to 0 as the special case of this expression, we can see this would be same as the third equation. That means in 3D irrotational flow, these three equations are not independent of each other. There's a redundant equation. So in this case, we have only two independent equations based on the assumptions for 3D irrotational flow. To solve the three velocity components, we need an additional equation. So this is same as in the 2D case. And we will see the additional equation is the continuity equation. For irrotation flows, there exists a velocity potential function phi, and from which the flow velocity vector v can be calculated as the gradient of the velocity potential function given as this. The simple reason for such a velocity potential function is because if we calculate the core of the velocity vector, we have the expression as this. So this is identically 0. This is a simple proof for irrotational flow, the existence of a velocity potential function. In the Cartesian coordinates, three velocity components can be given by the partial differentiation of the potential function phi with regard to x for the velocity component u around x-axis, the velocity component v around y-axis, and the velocity component w around z-axis. Thus, we can see the first advantage for irrotational flows, since three velocity components u, v, and w are reduced to a single scalar function, the velocity potential function phi. Now we consider the incompressible flow. The continuity equation is given as this. The divergence of the velocity vector is 0. So if we take the velocity component from the velocity potential function into this continuity equation, we have the expression as this, and the first term of the continuity equation become this, and the second term become this, and the third term as this. Therefore, we have the new equation for the velocity potential function phi given as this. If we consider the 2D irrotational flow, the continuity equation is given as this, and the corresponding equation for the potential function is given this. These are the Laplace equations for 3D flows and 2D flows. If we use the Laplace operator, the Laplace equation can be more simply expressed as this. Here, the Laplace operator is given as this. that is the Laplace equation as this. In 2D case, the Laplace equation would be given as this. Thus, we can see for potential flows, the dynamic equation, the Laplace equation can be obtained from the continuity equation. Here, we have the second advantage for potential flows. The dynamic equation for incompressible potential flows is linear partial differential equation, the Laplace equation for the velocity potential function phi. As we have seen from the previous slide, for a potential flow, the assumption of an irrotational flow would simplify the flow dynamics problem significantly. Based on the reference, we can see the assumption of a irrotational flow is a very strict assumption. But the assumption works very well for many practical problems, many more than we think. This is why the potential flow theory is so important and so useful in fluid dynamics. It still is. This is especially true before the computers are used for solving Navier-Stokes equation. So as we have mentioned, with the assumption of an irrotational flow, the velocity component u, v, w would be reduced to a single scalar function. So the advantage would be 3 partial differential equations versus 1 partial differential equation. And the dynamic equation is a linear equation for incompressible flows. Thus, we have the advantage if we compare the nonlinear partial differential equations, the Navier-Stokes equation, with the linear partial differential equation, the Laplace equation. And also, for linear partial differential equations, their solutions might be made using the superposition method. And this will bring the huge mathematical advantage in the solutions of the dynamic equation. In the previous slides, we already built the dynamic equation for the potential flow. To solve the dynamic equation, the Laplace equation, we need to specify the boundary conditions for the problem. This including the kinematic boundary condition. For instance, to specify the fluid velocity on the boundaries. The most used boundary condition is the no penetration body condition. The mathematical equation gives the boundary condition as this, or as this. This means the normal velocity on the boundary is the same as the normal velocity of the body motion. That means there is no fluid penetrating into or leaving the boundaries in the normal direction. Here, n is the normal vector pointing away from the fluid, and the vector Vb is the body motion velocity. If the structure is fixed, then the body motion Vb would be 0, given as this. The second kinematic boundary condition is for the lifting body, so we need to specify the velocity at some specific point. For instance, the Kutta-Joukowski condition for lifting bodies. At the trailing edge, see here, if we have the velocity come from the upper surface of the lifting body and the flow coming from the lower surface of the lifting body. At the trailing edge, we have two different velocities, V1 and V2. Obviously, this is not physics, only when V1 and V2 are both 0. That means at the conventional trailing edge of the lifting body, the velocity must be 0, V1 equaling to V2 equaling to 0. However, if the lifting body has the collapsed curves the trailing edge, and the velocity come out from the up surface and the low surface are both tangent to the trailing edge. In that case, we will have a certain velocity, but V1 must be equal to V2. So the Kuta-Rukowski condition are only used for the lifting body in case the potential flow can generate the lift on the body. And we may also have the dynamic boundary condition. In that case, we need to specify the force or the pressure on the boundaries. For instance, the dynamic boundary conditions for the free surface, like waves. And on the free surface, we can define the pressure as P0, the atmospheric pressure at the sea surface. So this is the very useful dynamic boundary condition if we study the wave and structure interaction. Now we will see how the Bernoulli's equation for the potential flow is derived. For the potential flow, the fluid dynamic equation is the Euler equation given as this. This part is the fluid gravitational force, but it is in opposite of the z direction, thus the minus sign here. In the derivation of the Bernoulli's equation, this convective acceleration term is the most difficult one. Here, for deriving the Bernoulli's equation, we can use the vector calculus identity. The gradient of the dot product vector A and B would be given as this. Now we can let vector A equaling to velocity vector v and B equaling to the velocity vector v. Then the vector calculus identity would become as this. Now we can apply the definition for the potential flow. The core of the velocity vector is 0. Thus, this term would vanish. Therefore, the convective acceleration term would become as this. Now we can look at each term in the Euler equation. The first term, the local acceleration, and if we substitute the velocity vector calculated by the velocity potential function into the expression, we have expression as this. And we can change the order of the operation, the partial differentiation with regard to t and the gradient, the Laplace. So we have the expression as this. And in the previous slide, we have already obtained the convective acceleration given as this. So we have the expression as this, the gradient of this expression. And we can also write this into an expression as this. And for the body force term, if we make the gradient of the function rho gz, and we can calculate this gradient as this. Obviously, we can see this term would be 0 because rho gz is independent of x. Same for this term, rho gz is also independent of y. So we have only one term as this. So this will give the result as the rho g unit vector k. So put all this together. For the irrotational flow, the Euler equation can be written as this. And we can see both sides are calculated as the gradient of the expression this and the expression of this. Now if we move the term on the right hand side into the left hand side, so we have the expression of this, the gradient of this expression. So if we integrate this expression, we could have the integral form of the Euler equation for the potential flow given as this. Here, C0 is the integral constant, but it can be time dependent, because if we calculate the gradient of this expression both sides, and we would have the expression as this. And for a steady incompressible flow, the Bernoulli's equation would be given as this. And here, C0 can be given as P0, as the total pressure, defined as the pressure of the static flow at Z equaling to 0. So this is very similar to the conventional Bernoulli's equation.